All right. Hi, everybody. Thank you so much for coming out. This is the third and final data bootcamp in the 2018 Space Apps Challenge Data Bootcamp series. My name is Joe Spence. I'm the Executive Director of Space Apps NYC. We are a nonprofit grassroots organization here to host the NASA International Space Apps Challenge. It's an international hackathon that we run every year, and tens of thousands of people worldwide come together in one weekend to solve challenges in space and science exploration. Hopefully you've all gotten links and registered, because that's where I've sent all the emails. So if not, come chat with us afterwards. I'm just going to give you a little rundown of our organization, what we're here looking to do, and then I'm going to intro some of the other speakers and we can get this rolling. So I want to start off with a testimonial from a hacker from 2017. And if any of you have been to a previous boot camp, I recognize some faces here. Apologies, we're going to run through some of the same material. But this is a fun video. I'm really glad we have it. And we're going to talk about some of the points in here. Hopefully the audio works. Whoop. Everything's inverted. Give me a second. I got to reorient myself.
5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
I mean, NASA is attached to it. Who doesn't want to participate or work with something NASA related?
I already had been to several hackathons, and I thought Space Apps was the perfect combination of the cutting edge software development and the APIs out there connecting to the next grand frontier, which is space. So it's really exciting.
I feel really happy, proud of myself that I decided to come, wake up at 6:30 to get here and hack all day. I feel really proud that I'm doing this and I'm only 10.
We've had the good fortune of getting a diverse range of skill sets on our team, as well as age ranges. We have a high school student who's coding our front end, and we've got some very experienced software engineers.
There's so many diverse groups of people that come here with their own mindsets. So I feel that's perfect with space because there's so much to discover.
Just because you're young doesn't mean that you have less ability than others. Even though you may feel like you have less potential because you're younger, it doesn't mean that you're not capable of the same things. I have a lot of kids in my school that say, oh, I just get in the way because I don't know how to code. But the point of coming to hackathons is learning that you won't be in the way and learning that you can code.
I went to space camp when I was a kid. I have been into NASA and space. I saw a shuttle launch when I was a kid. So it was really cool for me to be here and see the stuff that folks are working on.
People can come here with virtually no programming experience or haven't seen any line of code before, and you got to realize that it's not really about coding as it is about just a really great hub for ideas and entrepreneurship. If you have a great idea, come here and see what you can do.
Go get up, hack. It's really fun.
Five, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Sorry about that. I miss mirroring. You made it harder, my guys. Yeah. Okay, cool. All right, we made it. We're good. Everything okay. So the Space Apps Challenge has been around for 7 years. This is the 7th event we're going to host. We're going to host it here at the Lower East Side Girls Club, and Dave will be up in a minute to talk about the amazing space they have in the planetarium that we're going to check out a little later tonight. But this year we're on track to break all records for participation in the Space Apps Challenge. Last year we had 25,000 people worldwide participating in the largest worldwide international hackathon. Over 187 cities in about 70 countries, and again, we have hundreds of cities right now registered. This is an event where you could literally hack with people all around the world because you're working at the same time, working on the same challenges. All right, I'm going to do one more video and then we're going to skip through some of this. So this is a demo from last year that actually won locally.
As our ability to harness the sun's energy matures, our tools must also evolve. Proxima is the next generation of intelligent power management. Using machine learning, Proxima grows with the mission by anticipating your needs. A leap over current systems, Proxima empowers your crew to make critical decisions before the storm hits. Proxima delivers knowledge when and where it's needed. A powerful dashboard illuminates key information to support confident decision-making in demanding situations. In an emergency, users can respond using the decision support system to keep critical operations running. Proxima is designed for Mars but has applications here on Earth. From commercial farms to forward operating bases and remote villages, Proxima powers a bright new energy future.
Music really kicked up there at the end. That's a video that the Proxima team created themselves. If you win locally, you then create a 30-second, I believe it's 30-second video to then send to NASA, and NASA looks through all these things to determine who's going to win globally. This is an example of a project that was worked on last year, and then you guys will be working on this year. Just an example, it's not going to be as polished as this for the demo on Sunday, but just keep in mind there's a lot of videos out there of past projects. This is one of those situations where you could see like past tests that your professor has given out to previous classes. You can go and read up on those and see what other people have done to compare and to really scope the kind of projects that you're going to be working on this year. I assume all of you have some basic understanding of the tools you'd be using because we're here at an OpenSpace talk. We're going to talk more about OpenSpace in a second, but it's another great tool that you could use to create some really powerful demos. And we're going to be looking at some of the really cool visualizations later. Let's skip over. Okay. So just another quick recap on Space Apps NYC. We're here to host space tech events. Not many other organizations do that. Not many people in the tech community understand that there's a space community in New York. And so we're here to really open the door to anybody who's interested in space. If you've been interested in space or science since you were a kid or even recently but don't really know how to break into the industry, this is one avenue for you. Is we partner with space science organizations across the city, whether they're space accelerators, citizen science organizations, more accelerators, the Internet Society. First Robotics is doing a competition this year. It's for high school students. If you know any high school students who are interested in doing robotics, that's a great one. It's going to be space themed in 2019, so obviously we're super excited about it. We're looking to put on, as I said, tech events, but we are looking to broaden to anything space and fun related. So definitely go to our website, spaceapps.nyc, sign up to the mailing list because we're going to be having more events throughout the year, social events, tech events, meetups, panels on space law or asteroid mining, a lot of really cool stuff going on in the city. And these are just some examples of events that we've done. Doing the Space Apps Challenge. You guys are all familiar with the Bootcamp. Like I said, I've seen a few of you at some of the past ones. We did a Expanse finale, season finale party. It's a really great TV show on Amazon Prime. I recommend you go check it out. A kickoff cocktail party with Women's Sphere where we did a cocktail workshop and you get to mix your own cocktails. And also we co-hosted the first museum hackathon at the American Museum of Natural History, which was space themed. So we're trying to really branch out into all the different boroughs in New York, work with different organizations to bring you really cool events. And So that's just a little plug to come join our organizing team. We're all volunteers. We love doing this. It's really fun putting on events. It's really fun putting on events related to space for people that we know that come back every year. So if you're interested in participating, getting a little bit more involved than just showing up, come chat with us. We're always looking for an extra hand. And this is, we're not looking for sponsorships right now, but this is just an example of organizations that we've worked with in the past to bring us really cool events. This year, our intergalactic sponsor is Google Cloud, but we've also had not just tech organizations, but space organizations coming and sponsoring a hackathon or other events because they recognize that there is this growing community of space enthusiasts in New York that have engineering and STEM backgrounds that have not previously been involved in the industry but are really there, ripe for getting involved. And that's it. This is my contact info. I recommend going check out the YouTube channel, which has updated. I got to fix that. It's just at SpaceApps NYC. We got hundreds of hours, 100+ hours of videos from past demos, boot camps, presentations. We've done space conferences in the past. We have a lot of really great talks. I highly recommend going and checking those out, not just to gear up for the hackathon, but also just because they're really fun. And hit us up on Twitter. And with that, I'm going to hand it over to our next speaker, who is Hannah Payne. She is from Women's Sphere, and Women's Sphere is a co-organizer of this year's Space Apps Hackathon. Hannah? Teamwork.
Cool. Hey everybody, I'm Hannah Payne. I'm program director for some of the programs at Women's Sphere. It's good to see a lot of familiar faces over here tonight. So like Joe said, I will try to keep this a bit short and get to the demo. So Women's Sphere is an organization founded in 2007 dedicated to improving the world by empowering women and girls. We have focused primarily on people in business and also in STEAM, so science, technology, engineering, art and design, and math. And that's how some of our upcoming events are going to be focused on. Is anyone here a woman and a student? Cool. I'll be talking to you in a minute. So Women's Sphere has 4 branches. We have the Women's Sphere Innovation Leadership Lab and the Women's Sphere Incubator Network, and those are the things that are organizing the events that I'll be telling you about in a few minutes. Also, we have summits and festivals. It's currently Women's Sphere Fest month. We're going from November through October through November, with lots of kinds of events. We had a kickoff event with cocktails that Joe mentioned, and we have a whole bunch of other things coming up. Our summits and festivals are open to people of all genders, although our focus is on women, so we invite you all to those things. Additionally, we have our foundation, which supports organizations like this, and space apps, things like that. Just what I just said. We are thrilled to be a sponsor and co-organizer of Space Apps. Additionally, we have a strong connection to the Philippines, where our founder and CEO is from. And we will also be simultaneously organizing the event in the Philippines while the New York City event is going on. So we will be getting up at 8 in the morning so we can do 8 p.m. presentations for the Philippines people who are 12 hours ahead of us. It's going to be very exciting. So we like having that connection, and we want to build more. One thing we are especially excited about, in addition to all this awesome space stuff, are the UN Sustainable Development Goals. There are 17 goals that we are attempting to work on as a planet that range from everything from income inequality to protecting animals and plants. It's a great range of topics, and people have found really innovative and interesting ways to help us reach them. On that note, we have three-pronged event coming up that is centered around the Sustainable Development Goals. We are going to be hosting a celebration of STEAM all around the world. You can think of it kind of as a hackathon, although we are trying not to use the word hack. Students around the world can form teams and create projects either in video, the arts, or code that work to support one of the Sustainable Development Goals. So if you're a woman and a student, we really invite you to come participate. You'll have 2 weeks in November. It goes from November 1st through November 11th. It's very easy to write down, very easy to remember. And you'll have those 2 weeks to create a project that is designed around one of those goals. We think there's something really inspiring in each one of them, and we are really looking forward to seeing what people produce. After those 2 weeks, they'll be sent in for judging on our platform, made sure that you are in fact students who are producing them, and then they'll go to our global team of expert judges. After that, we will have our finalists and our medal ceremony in March, which will be very exciting. So if you are a student and a woman, join that. Currently going on is the Women's Sphere Festival. I mentioned it earlier. We have a number of events coming up. So if you watch Women's Sphere on Twitter and watch our website, you'll see a lot of things designed around women and innovation and STEAM that you can check out. One of the things we're excited about is the Emerging Leaders Summit, which will be in November. And that brings together all different kinds of innovators and change makers to meet either with professionals, we have one for professionals and one for students, and that will get you together to become better leaders and become better organizers in your communities and on your teams. So that's another thing we're extremely excited about. Yeah, that's it. We are excited to be part of this, so thank you so much.
So welcome to Lower East Side Girls Club. Thanks for coming. Some of you have been sitting around patiently for a while tonight. I hope you all come back for the Space Apps Challenge all weekend, Friday and then Saturday through Sunday. If you have any questions about the Girls Club, you can ask me, or you can ask Lynn, who's sitting back in the back. There she is. She's really the driving force with her team of getting this building built, and we've been here 5 years. So our plan tonight is to go upstairs first to the planetarium, and Micah's going to show, where's Micah? Are you right in front of me? Yeah. Micah's going to show us OpenSpace, the new software that he and Carter Emmert and some other coders, programmers have put together, and then we're going to come back down and he'll do more technical dive into it. It'll be easier to see the whole interface and configurations back down here. So we'll do a quick blip upstairs. You can see that, and since there aren't that many folks here, if once we're done with both of the sessions, we can do a quick tour of a couple of other places. You can kind of get a preview of what's going to be happening this weekend. Okay, cool. Let's go upstairs.
And for people who are on the stream, we're going to try and stream from upstairs, so just hold on.
There's a few of us, a few enough of us that we can kind of bunch in the middle of the rows. So if you're the first one to go, just pass the middle.
Okay. Hello, hello. All right. Everyone can hear me, I would imagine.
So you want to sit close to the middle, that's the best view. But, hey,
All right. Oh, we were talking about maybe this, right?
Yeah, I'm thinking maybe this.
Okay, yeah. That's okay. Yeah, that's okay. It's like maybe I turn my hat a little bit. I'll survive. Hello. Microphone check. 1, 2. What is this? Hello. We are looking at the moon. Yeah, it'll be hard, but I'll make do. I don't need to point out any individual craters or anything, so I will survive. Everyone is looking at the moon right now. Hopefully, you recognized that. And then I'll just wait like another 1 minute to see if people are still coming in. And maybe we will zoom out. So, some of you maybe have seen OpenSpace before. Some of you maybe have seen software like it before, but then maybe some of you haven't. So, a little bit about OpenSpace, which I'll talk more about what it is and how it came to be and all of that later when we're downstairs. But basically, we are showing the space, we are showing the solar system, we are showing the galaxy, we are showing the universe. And basically everything that you see in here is data driven. And that's one of the big things of OpenSpace is that we are not artists creating models and stuff for Hollywood movies, but rather we are trying to visualize science through cutting edge techniques in data visualization. And I will talk a little bit more about that later. So basically, I'm going to do mostly in the solar system here, and then we'll leave a little bit. So we're starting out at Earth, Moon, and the Earth-Moon system. Here you can see the orbits of the Earth around the Sun and the Moon around the Earth. If I want, I can easily, I can go here to my virtual properties, show the trails, hide the trails. So, maybe you want to do something without those orbit lines, you can just turn them right off. So, we'll start I will focus on the Earth, and we will zoom into it. So one of the things about OpenSpace is about our navigation model is that you always have to be looking at something. So space is very large, and if you let people just fly around, they get lost because it's really hard to find things, especially if something like the trails are off, right? How many people can see the moon right now? Probably not, and if I zoom out, you won't be able to see the Earth. So you always are focused on something, and then you can orbit and look at that thing. So you can orbit around it, so I can go around the Earth, I can tilt my look, but the Earth is what we're looking at right now, and we're actually looking at the weather that is loaded from a satellite from NASA, and it's one of the features of our globe browsing module, which I'm going to talk a lot about later, is the ability to add in these different layers of data. So the version that we have right now, it's showing the weather loaded for each day. And then as you would zoom into the Earth, the weather would go away. And if I was over land somewhere, the land would appear. Unfortunately, there's a lot of ocean on our planet, so I seem to be always over an ocean. But our map data set for the Earth comes from Esri. And, it's similar to something that you would see in Google Earth, where as you zoom in, it's loading higher resolution versions of the tiles that you're seeing, and it combines the imagery with a digital elevation model to create a texture and a model for the surface, so that when there's mountains, you can see mountains and see the relief. So right here, we're looking at the Earth and a map of the Earth that is provided by Esri. However, we can do the same thing on other planets. We can do the same thing on the Moon. We can do the same thing on Mars. And I think that we'll spend a little bit more time looking at that rather than the surface of the Earth, because you guys are on the Earth, you've been there, you might have seen Google Earth, you might have seen some pictures of the Earth before, but you've probably seen less of the Moon and Mars. You'll notice that maybe the Earth wasn't up. We always talk about what is up really, though. So I'm going to zoom us out and take us to the Moon. We're going to look at the Moon and talk about some of the data that we have on the Moon. So if I go to the Moon, I'm focusing on the Moon, and then I will travel there. So here we are. So our Moon is shaded right now by the shadow of the light from the sun is showing. However, often when we're trying to show the Moon, we kind of want to show the whole thing, right? We don't want to be like constricted by what is really happening out there. So I can easily do things like this, and maybe downstairs later I will show how to use these menus and stuff. You know, another thing I could do if I wanted is that I can control time. So if I did want to see a portion of the Moon but still maintain the shading that we have here, I can actually just move time around, and if I go fast enough, we will see that, you know, based on where the sun is, the lighting changes on the surface. And so, you know, for certain visual effects, you will need that. So what you're looking at right now is a global mosaic of the Moon. This is imagery that was taken by the LRO, the Lunar Reconnaissance Orbiter, and it was taken by its wide-angle camera. So that mosaic was then put together into what we call a geotiff, which is an image file that has geographic coordinates built into it. And I will talk a little bit more about that later as well. And then it is also embedded into the TIFF different levels of resolution. So as you see here, as I zoom in, the resolution will load in higher and higher detail depending on where you are. So I'm going to zoom in, and then that will load up, and just depending on your connection, it will load faster or slower. And then you can also enable caching, which I'll talk about later, so that when you've already downloaded the tiles, the tile will be there on your computer. So the imagery was coming from the Lunar Reconnaissance Orbiter and its narrow-angle camera, but you'll notice combined with the imagery, we also have a digital elevation model. So that is the height of the surface of the planet at any given location. This one that you're looking at came from the LOLA, the Lunar Orbiter Laser Altimeter. So basically, they're just going around shooting a laser altimeter down from the craft. And, you know, when it comes back, you can imagine how it works. If it comes back quicker, the surface is taller, and if it comes back slower, the surface is not as tall. So these, the elevation model is loaded in as well. So these layers that you're looking at are loaded in over the internet. Basically, we take a web server and we have it serve up the tiles, and it can chunk out the image based on XY coordinates, and then OpenSpace, as we browse around the globe, will ask for the image at this XY coordinate and then render it. So we have a series of global maps for each planet. Different planets have different ones that are of, you know, some of the planets that we don't have all this data for, we just show an image and we don't have all the data. When we do, so here I was just turning on another one. However, maybe it's going to take a second to load in, so I won't even bother with that guy. So we have a certain amount of imagery that we bundle with OpenSpace, and these are these layers like this one you're looking at that will load in. However, we also can locally include on to the computer running OpenSpace high-resolution patches of data that is either too big to be streamed over the internet or is specific, and we don't necessarily want to bundle with the whole piece. So what I'm turning on now, which is like very hard to see if you don't know where it is, but as I will go in, it will show up. So what I'm going to turn on is a local layer of the Apollo 15 landing site. So whereas the global mosaic of the moon that you're looking at was loaded over the web, this local patch of the Apollo 15 landing site is actually existing on disk on this computer. It's the same TIFF file, or a similar TIFF file, only rather than being chunked out by a web server and served to us over the internet, it exists here, and OpenSpace is able to load the whole file at once. So that's why I can turn it off and turn it on, and the image is instantly available. It has the advantage of you don't have to wait, but you know, it's they are a lot larger, and we have, for various different portions of different planets, we have an exorbitant number of gigabytes of these files, so we don't bundle them all with the default installation, and it's up to you to then go and download extra parts. So one of the things that I'll be talking about later is how does this show up, and how does OpenSpace know to look for this, and how is OpenSpace able to render it, and what type of information do you have to provide. So I won't actually like give the whole spiel about like when they landed and where they went and all these different things and this lava channel and stuff, but what I will just try to briefly do is show this strip that we're looking at was taken from the Lunar Reconnaissance Orbiter narrow angle camera. So you can see it's much higher resolution than the imagery around it, and it's so high resolution that we are able to actually see the lunar lander on the surface of the moon here. So I've kind of got it right at towards the bottom of the dome, and you can see this black spot here. And then now you can, as I get closer, you can actually see these trails. So this is where they landed, and then the trails over to the rover and the science experiment. So you can use this feature of the globe browsing to provide more details about specific portions of the body that you are trying to present about. So whereas here, if we were giving a presentation and showing stuff about the Apollo, we might show this landing site, and we might talk about what they did and where they went. Maybe later you want to give a presentation about the geology of the moon and how things were formed. So you might want to include a layer that shows the chemical composition of the surface, or you might want to show a layer that shows the colorized relief. And one of the things that I'm going to show later is how to download a strip like this, process it, and then make it show up on the globe. Basically, the globe browsing is a very kind of a compelling feature that we have of OpenSpace because it provides something that's familiar to people. They understand planets and mountains and things like that, and they're kind of used to looking at the moon, so everybody really enjoys the globe browsing. So adding new layers and new data and information to globes is a really is a thing that we do a lot for our presentations, and I imagine it's something that people will do for the hackathon. So I will maybe show a little bit of globe browsing on Mars as well, just because it's nice, but I don't really want to spend too long talking more about a different instance of the same feature. So on Mars we have more maps than we do even for the moon, and we have higher resolution imagery for some parts of the moon. So here again you are looking at the wide angle camera. This mosaic was created with the wide angle camera, and then I can turn on various different layers of that were made with different cameras. So now I'll turn on this one, which was created with the context camera. And you can see with this map, we actually only have 70% of the surface created, but this map has 6 meters per pixel resolution. And now you can start seeing some of these channels and stuff, and it will load in a higher detail as you approach the surface. For Mars, again, we have many global maps that are loaded over the web, and then we also have some local patches that would just you can turn on and they're there instantly. I actually don't know this one that I just turned on where it's located. So, oh, there it is. So if you see this one, I have this one shows up immediately because it actually lives there on disk. This local patch was actually created by a set of high school students that we had working on processing this data. I will talk a little bit about how this patch was created. It was done with a little more complex process than the one I'm going to show, but it was created from the raw images downloaded from NASA's PDS. And when I turn on the surrounding mosaic, you can see it kind of fit in. So the globe browsing is really kind of an awesome part of OpenSpace, and I expect that a certain amount of people involved in the hackathon will use it. I would like to now just kind of exit it and talk a little bit about some of the other data that we bring in and features. So, are there other bodies other than planets, you mean? Yes. So, that's a great question. So right now, like, we only have planets that you're going to see. However, one of the other features of OpenSpace is the mission visualization. And so for something like the Rosetta mission, I believe it was the Rosetta mission, where they went and they visited an asteroid, we then, as part of that mission visualization, have the asteroid, and we have the model of it, and then what we have is the pictures that it was taking projected onto the model of it. So it's actually a great segue into the next thing that I wanted to talk about, which was the NASA SPICE data. One of the big parts of the OpenSpace is how we use NASA's SPICE data. So this is their data that they generate about where all their spacecraft are and what they're doing, but it also gives us the positions of the planets and any bodies. So whereas you see Mars right now and you see its orbit lines, and then when we zoom out, you can see other planets. The way that OpenSpace decides where these things go is by taking the data from NASA and using it to position it over time in 3D space. And so if we wanted to bring in other bodies other than planets, we could use, if NASA has data about where those bodies are, we could use that. We also have some other ways of elements in 3D space that I can talk about when I'm downstairs later, because somebody else asked about that as well. So I'm going to now take us to Mercury and show a couple things that we showed in a presentation a few months ago at the Hayden. Here we oh, it's already turned on. That is great. I will actually just turn it off though. So here we are at Mercury, and you're actually seeing these blue lines. So what are these blue lines? So this blue line is the orbit trail of the Messenger spacecraft. And if I focus on Messenger, we should actually be able to go and zoom in and see the spacecraft. So both the spacecraft, along with these orbit lines, are generated using the SPICE data. So here we are, we have a model of the spacecraft, and we have it positioned. So the system clock of my computer, well, not the system clock of my computer, but OpenSpace's clock is actually set to May 17th, 2011 right now, because that was the time when Messenger was orbiting Mercury, and if I go forward or back in time, we can see it move around this orbit. So let me actually, I don't think I will actually do that now because it might mess with our camera angles if I didn't set it up right. So here, if I zoom out a little bit, so here's Mercury, and then we have our orbit around it, and we have our spacecraft. And one of the things that I will talk about downstairs is how do we bring spacecraft in, and how do we not only show it, but position it and tell OpenSpace where it is and what it's doing. The presentation that we gave about Mercury was about this messenger spacecraft and about different data that it collected. So we showed the craft, and we showed its orbit, and we showed it coming in and orbiting Mercury. And then we also showed some high-resolution patches of Mercury that where we went to the surface, and just like on the Moon and Mars, we can go and we can browse the surface. We have our loaded map layer, which is loaded over the internet. But then again, the same thing. We had local patches, and then I believe that for Mercury, maybe I can also, there's Mars, Mercury. Maybe I can turn on one of the other maps because we had some maybe colored ones. So let's see if this guy wants to show up. So here we have added in a magnesium map. So this is the composition of Mercury. This is the abundance of mercury, well, on the planet magnesium on the planet Mercury. So you can see the red parts are where Mercury is more abundant, the blue parts is where it's less abundant, and this is the type of data that you can bring in and use in OpenSpace. So this data was previously not in OpenSpace before we gave the presentation. We worked with our planetary geologist who was our co-presenter, and he provided me these maps, and in 5 minutes I was able to put them in. So his maps were actually just JPEGs that were projected in a equirectangular fashion, and so they're able to just map right onto our sphere, and you can see some of them are missing data in certain places. But this is an example of an easy thing to kind of bring in and add in, and it really adds to the science visualization, and that's the idea of some of the stuff I'll be showing. So those were some of the colorized maps that we had added. And then another cool thing that we added was the magnetosphere of Mercury. So that was what was on when I first came in here. So let me turn this on and let me zoom us out. So here is the magnetosphere of Mercury. It's rendered as a volume, and it's rendered using our volume rendering module. One of the reasons that I wanted to show this was to give an example that I could then talk about later about how different types of data are rendered using different modules inside of OpenSpace. So this volume rendering of the magnetosphere uses our volume rendering module. It's actually quite interesting because aside just from like looking cool, there is some interesting science that can be determined from the visualization of the magnetosphere. So one of the interesting things, so first off, you're seeing that it's being pushed away from the sun by the solar wind. So here, you know, if you look at where the sun is with Mercury, it's pretty clear that it's pushing it away. But then you also see this interesting pinch that's happening in the north and south poles. And if I zoom in, you can see it. You can actually like see above and below. There's like it looks like someone's fingers are kind of pinching it. And that's, I don't even remember what the explanation was from the planetary geologist, but basically something about its poles. Then another interesting thing which we actually had to adjust some parameters of the visualization to see. So I'm not sure if I'm able to appear, if you're able to see it here, but basically there is a disk that forms behind the planet, like a plane of a higher concentration of magnetic activity that it was like theorized, and then when the measurements came in, it was they had discovered it, and then when we did the visualization, you could see it, and so there is interesting stuff to be either demonstrated or proved through the visualizations. Okay, so we saw some globe browsing. We saw this interesting magnetosphere, and we looked at some of the ships. So let's now kind of zoom out, and let's maybe leave the solar system for a moment. So basically, we could go visit any of the planets in the solar system, but only Mars, Earth, and Mercury right now actually have like globe browsing layers and maps that are built into them. So now we are going to zoom out, and once we get to 1 light year away, our sun just turns into a star like the rest. And now I'm zooming out, and we can start seeing the stars in our local group. So I'm actually just going to turn them up a little bit because I had done this previously here, but I'm launching a different scene which didn't have my setting of them turned up. One of the things that we do in OpenSpace is based on the dome and the lighting. We might adjust different parameters to make certain things more visible and certain things less visible because based on the contrast ratio of your screen or your projector, etc., different things have to be adjusted because so that you can actually see what's going on. So here we're looking at a lot of stars. So one of the things, so this again is data that is represented. So we have our digital universe catalog, which is created by AMNH. All these stars came from there, and it provides the positions, the colors, and many other various properties. One of the things that I will just talk about downstairs as an example is how someone can bring in different data sets of stars. So this is our default one that we ship with, which was compiled and created by some astrophysicists at the Museum of Natural History, but there are other ones, and maybe you want to show them. One of the real interesting new features that has been put into OpenSpace, not in this version, but I'll talk about it later, is the new Gaia Data Release 2 dataset, which has 1.7 billion stars in it, released by ESA. And we have someone that was working on rendering that, and we have a really interesting, compelling version of rendering the Gaia database. So, so we could spend some time looking and talking about the stars. Some of you guys might know more about some of these stars than I do. But if we zoom out away from the stars, I will actually zoom out. Actually, before I zoom out here, let me turn on 2 of these things.
Focus still the sun.
So the focus is still the sun, and actually, I'm actually gonna actually exit us and relaunch for a second because I am when I loaded up the Mercury magnetosphere earlier, I actually loaded up a version that does not have the rest of the galaxy in it. So this is a great kind of example of some of the stuff that I'm going to show later about how you set up what is in your scene and what is showing on the screen in OpenSpace. Basically, you saw a couple different things, but we have lots of data, and we have lots of modules, and we have lots of capabilities, and we don't always load up all of the capabilities into the scene at once. So that was actually the scene that I had made for the Messenger program, so we didn't actually load up the rest of the galaxy in it because we were not going beyond the stars of our solar system, beyond our solar system even, much less the stars of our galaxy. So now that I have this other version loaded up, I could show maybe some other interesting things, like briefly, I will just show the constellations because later I'm going to give an example of how these are shown on the screen and use its asset file as an example. So here are the constellations. I don't really need to talk about them too much. You guys know what they are. People get interested when you zoom away from the constellations and you can see them move, right? Because they're made up of stars of various magnitudes. And then I will just kind of turn that off. Okay, so now we were going to go, another interesting thing to turn on, a data point, is this equatorial sphere. So this is what we call the radiosphere. This is supposed to represent, how far our radio signals have traveled since they were able to emanate past our atmosphere. I could do something like interesting, which is turn on the star labels here, so you could actually see which stars will have received our radio signals or not. And I can later talk about how these star labels show up. So I will turn that off, and now I'm going to go into the universe, turn on some galaxies, and we can go and see the galaxies. So as I zoom away, those are the stars in our local galaxy area, and then we kind of zoom away to the image of our galaxy. As you might guess, this is not actually an image of our galaxy because we're not able to take pictures of our galaxy yet. So this is one that is similar to the galaxy. I forget what name it is, but it's one that we think looks very much like ours. So as I zoom out, you're seeing these dots appear. Each dot is now representing a galaxy, and what you're seeing is data from the Tully Galaxy Survey, which is one of the galaxy surveys that's included by default in OpenSpace. We include about 10 different galaxy surveys. I believe that I'm only going to turn on 2 right now. So, again, I don't actually need to tell you about how many stars are in each galaxy and how many galaxies are in da-da-da. I'm going to talk more about how this gets in there. So basically the galaxy surveys are working similar to the star surveys. We have what we call a spec file, which describes their positions in space and some of the other properties associated with them. So as I go away from that galaxy survey and I zoom out, you see another galaxy survey coming in. This is the Sloan Digital Sky Survey. This is, I believe, to be our most detailed survey of the galaxies. It has the interesting kind of data point of why is there stuff missing on the sides? Well, that's because we can't see out there. Why is there more on the top and the bottom? That's because we have more telescopes in the northern hemisphere than the southern hemisphere. But, one of the interesting things about this survey in terms of bringing it into OpenSpace and the data is that this is one of the ones we have that fades in and out as you zoom in and out. So that way, in the asset file that includes the galaxies, you could say, and only show this when you are this many parsecs away from the sun. So that way, you can have it on and not have all these things in front of your face when you're zoomed in, but then when you zoom out, it naturally appears. Past the galaxies is the quasars, which again have a similar thing where when I go away, they show up. One of the things that we actually have to work on is that what you're looking at is a fisheye rendering of OpenSpace, which actually renders 4 view planes and then combines them. And it turns out that the camera position uses one of the view planes instead of an average of them, and so this guy doesn't actually fade in as soon as we want it to when you're viewing this type of rendering. And I'll talk a little, I just wanted to bring that up so that when I'm downstairs, and I will talk about the configuration file and some of our different methods of rendering. So the last part of our kind of universe example is just to turn on the cosmic microwave background, which, again, like maybe some of you guys could even describe it better than I could, but we have that here kind of mapped around our image of the visible universe, and you can adjust everything that you're seeing. You can kind of adjust these properties of transparency and brightness, and many different assets have different types of adjustments that could be made. And later, when we look at the asset files, we will see how those adjustments are specified and how which different types of things have which types of settings and adjustments that can be made. So now we're going to kind of zoom back in. One of the features I'll just mention briefly downstairs, and I can link to some papers about it, is basically this concept of a dynamic scale of our scene graph, because we just traveled, an exorbitant distance that is unfathomable, but it looked like we were traveling the same speed as we are now when we were traveling a much smaller distance, which is still pretty large, I would say. And so, that was actually the topic of a scientific paper about how we handle this both traveling between distances, but also positioning things at certain distances. So how could you be on the surface of Mars or the surface of the moon and be calculating the positions of something on the surface of the moon, and then at the same time be seeing the stars in the background and calculating the position of the stars, because the level of precision that you would need would vary as the distances grow. So we have to deal with things in a interesting, dynamic fashion. That's not really a detail that you will need to know when you're trying to hack things into OpenSpace, but I wanted to give it as an example of some of the kind of research that is done through OpenSpace in terms of data visualization. So I kind of just brought us back to the moon, and that was kind of most of the things I was going to show, because basically what I want to do next is, when we go downstairs, talk about all the different things we saw and how they came into OpenSpace, and how you guys can bring things like them into OpenSpace using either the same modules or different ones. So if anyone has any questions or something they'd like to see in here, now would be a time to ask or say. Otherwise, we'll go back downstairs.
I had a question on positioning.
Yeah.
So I was just wondering, is this to scale the moon's distance, for example, to the Earth?
Yes.
Why don't you repeat the question first?
So, thank you. Yeah, the question was, is the moon's position to the Earth to scale? And so, I guess I would maybe challenge you by saying, what exactly do you mean by to scale? But I can tell you that it's accurate, right? So when you say to scale, which scale are we talking about, right? But it is, where it is, it's in our scene is accurately placed, whatever 500,000 miles or kilometers. I don't remember exactly what the distance is, but that scale and that distance is provided by the NASA SPICE data, which is their ephemeris data of where things are and when. But we, so I mean, it's accurate. Scale is an interesting concept when you're talking about these large distances.
A question just related to that. So you have satellites and spacecraft out there. Are those also displayed to scale, so you have to fly very close to it to see it, and then scale down the
yes.
craft? But then you say you want to also be able to see where you're going to go, like say the moon or Mars, in the same scene. Then
so I would say that yes, the spacecraft are positioned in that scale as well, in terms of you have to get very close in order to see it. I'm often flying through space, and one of the things that you'll see downstairs is on the interface, it tells you how far you are from the target. So I will fly to go to a spacecraft, and I'm I see that, oh, I'm only 300 kilometers away, I'm super close to it. Why aren't I seeing it? And then I'm oh, right, this thing's smaller than a car, you can't see it from 300 kilometers away. And so you do have to get close to it. What I would say about the reason I hesitated when you first asked about the scale of the spacecraft is that one of the kind of important things to get right when bringing in a spacecraft is the initial scale of the model. Right. So if you were to take that model, enlarge it in Blender, re-export it, then it would be larger in OpenSpace. And so you do have to get that initial scale of the model correct, and then from there it will, OpenSpace will handle the rest.
Could you, like you said, you could dynamically change the light that you're shining on the moon just to see more of it?
Yep.
And it's like not correct. When we see the space station from the surface of the Earth, it's lit by the sun, and we're looking up maybe 200 miles, 300 kilometers or so. So maybe if there was can you say I'm going to artificially light the spacecraft?
Yes. So,
bring it up so that I can actually see the
yes. So our one of the things that we added recently into our asset files, and I'll show this when I show one of the spacecraft asset files, is a light sources property. So right now we might just have two available, basically lit from the sun or lit from the camera. And then you can choose, basically we had to put it in for this exact reason because we were demoing, showing the spacecraft, and because of how we wanted to show the surface of the planet, then the spacecraft was dark. And it was like, well, we don't want to have to move time to jump between the da-da-da, so we'd like the option of being able to light the spacecraft from the camera instead of the sun. And so that's something we added, I think, really just about 3 months ago.
Why don't we answer some of these questions downstairs?
Yep.
It sounds like they're
Perfect, yeah.
They're more
Exactly. Yeah, because I will be showing some of the files and how exactly, I'll show exactly how that happens. Okay, so thank you for touring the universe in maybe a little more technical fashion than we normally give. And now let's go downstairs where I will talk about how some of the stuff that you saw came to be. Just
These seats are where you're going to be sleeping if you stay overnight. These are the prime sleeping spots. Why is that?
oh, that time was me ejecting the hard drive.
Yeah.
The first time it was updated.
I should. Well, we can turn it down without
The computer.
Yeah.
I just want to apologize to you for that. I had the sampling rate wrong on that camera upstairs, so it sounded like you were on helium the whole time.
That doesn't matter. I'm not too picky.
Otherwise, it was good.
Awesome. Yeah, I was thinking that I would need to stand over here because I'll need to use the computer. Hello. So you were going to ask, like, how does it compare?
Yeah, I haven't used that.
So, yeah. I mean, there is a variety of different software like this. Some that are very similar, some that are just similar in some ways, you know. One of the things that was interesting to me when joining this project was about a month or two after I joined the project, I saw NASA's eyes on the solar system. I don't know if you guys have seen that, but it actually functions similar to OpenSpace, and it has some of the similar data, and it has some of the similar visualizations as OpenSpace does. And I said to myself, wait, are we competing with this, guys? And then I realized, well, wait, no. NASA paid us to make OpenSpace, and they paid JPL to make that. So, like, why did they pay two different companies, two different people to make two different things that are so similar? And then I kind of realized, well, you know, we have some really big differences, even though at first glance they might be similar. But, like, for example, one of the big features of OpenSpace is the like variable configuration. And what I mean there is that we have built it to run on a variety of mediums. So OpenSpace works in planetariums. Eyes on the Solar System does not. So there's like a huge difference, right? So some software might be the same, but maybe he works in planetariums and maybe he doesn't, right? You know, another thing is like they have less precision because it's less about science and more about education. And so, you know, there is, I've been seeing various different suites of software. You know, another really amazing difference, which will be the first point of one of my slides, is that we're open source. And so being open source is really just kind of sets you apart from every other piece of software because of, you know, you could take it and do whatever you want with it and change it in any way that suits you, you know. Okay, so maybe I'm good to go ahead and just start here. Everyone, looks like everyone's here. So now I'm going to talk to you guys about how some of what you saw came into OpenSpace, and then how you can bring similar or different things into OpenSpace. So I've made like a basic presentation, but basically I don't want to, like, I will go through the presentation, but I also want to show during the presentations examples of what I'm talking about. And then after the presentation, I thought I would do one or two examples of just literally downloading something new off of the internet, running a few commands, and seeing it show up in OpenSpace, because hopefully that's the kind of stuff that you'll be doing during the hackathon. So what is the agenda? I will talk a little bit about OpenSpace, a little bit about hacking it, some of the details about the different hacking opportunities that I'll mention, and then at the end we'll give some examples. So as I mentioned, OpenSpace is open source. That is kind of a big thing for us, and you know, coming from a computer science background, it's something that really attracted me to the project when I was joining it. And you know, it's also, I always want to iterate to people that it's a data visualization software. So what you see comes from real data, and that's kind of another thing that separates us from other things. Like if you saw Mars in a movie, that probably wasn't created with data collected from the Mars Reconnaissance Orbiter. That was probably some guy sitting in a room making a 3D model of it, and then making a picture, and then adjusting the picture to fit the model. And while that might look really cool, being visualization from real data is something completely different. So OpenSpace is NASA-funded software. It's a collaboration between a number of universities and organizations. These are our four main organizations, which is the American Museum of Natural History, Linköping University in Sweden, NYU, and the University of Utah. We also have some other informal science partners, other museums and institutions that are using OpenSpace, but these are the main organizations involved, and we actually have developers working at each place. So it was created for visualizing cutting-edge science in a variety of mediums, such as planetariums. This is one of the things I mentioned. OpenSpace runs in a planetarium. It also runs on your computer, on your flat screen. It also runs on a touch table with a touch interface. It also runs on a Oculus Rift or a HTC Vive in VR. And so one of the parts of OpenSpace is our windowing framework, and that allows us to work in very different environments. So you can find out more about OpenSpace kind of on our website and about the institutions. It was started almost 5 years ago. We got our grant about 3 years ago when NASA saw our visualization of the New Horizons mission. Maybe that's something I can load up later. So we're actually on year 3 of a 5-year grant right now, and we're hoping that in 2 years, when the grant is complete, it will get renewed. I mentioned its data visualization. So one of the interesting things about OpenSpace is that it's not only is it a platform for visualizing this data and research, it's also a platform for doing research in data visualization. So each one of our partners there have master's students that do their thesis projects inside of OpenSpace, and their thesis project will be to add a new feature to OpenSpace. So the globe browsing feature that you saw was a thesis project of 2 master's students. Later on my computer here, I'll show rendering of the Martian surface from imagery that was taken by the Curiosity rover. And so that visualization, that rendering is done by a set of master's students who just finished their thesis. So some of the key features of OpenSpace are our mission visualization, which is basically the concept of, I'll use the New Horizons because that's the one that we got our funding for, but it not only to show the craft and where it is, but we can also show what it's doing and when. So in the case of New Horizons, it was imaging Pluto. So not only do we see the craft in relation to Pluto, but we can also render the view frustum of the camera as it maps onto the surface of the planet, and then see the imagery coming in real time. You could adjust the time through our variable time control to see, but so you can see actually how the imagery that we have of Pluto was generated and mapped onto the surface of the planet. So, you know, basically I just mentioned the variable time control. You could, it's a simulation, so when you are running OpenSpace, you are at a specific date and time, and that is how the positions of things are calculated. Basically, we have these files, these SPICE files from NASA that tell us at this time this thing is here, at this time this thing is here. But one of the interesting things about OpenSpace is that we have variable time control, so you could progress time at 1 hour a second. And you can see things zooming around because now we're going much faster. Or maybe you need to progress it at 1 day a second in order to see the planets orbiting around the sun, right? When we were looking at a visualization of the Gaia stars, one of the interesting data points of the new Gaia data set was some of the motion, the velocities of the stars. So we were actually able to visualize the motion of the stars in the Milky Way by turning on the data point of the motion and then progressing time at 500,000 years per second. So imagine every second it's advancing the simulation by 500,000 years, and where do these stars go over time? So globe browsing is one that I mentioned, is a big feature of ours. The dynamic scene graph is something I talked about, you know, about how that we render things at these various scales. And so I have a paper later that I can show as just an example of how some of the stuff that we implement then turns into a research paper about how data visualization can occur, and someone could take that research paper and use it. Maybe they want to visualize atoms and people. How do they, you know, visualize such a different scale of a person versus an atom in one of their cells, right? So they could use the same visualization technique that we use to render planets and stars to, you know, I don't even know if that's a similar scale or not, but it's certainly a broad range. I mentioned the multi-configuration display output. That's the concept that we can run on a computer, we can run on a dome, we can run on a table, we can run on a screen, we can just, if you can come up with it, we can run on it. We can run on a fisheye projector, on a regular projector. We can run in 2 windows, 1 window, right? And if we don't have that capability, we can add in a new capability. Another interesting feature that I didn't really talk about is the Lua script interactions. So the way that our GUI and our menu control works is that every time you press a button, it's actually executing a Lua script. We have a Lua interpreter inside of OpenSpace. For those of you who don't know what Lua is, it's a scripting language similar to Python or JavaScript. It's just another scripting type language, but you can actually use it to control OpenSpace. And there's certainly some interesting opportunities to be had there in a type of coding that is a little more accessible and easier to approach than the C++ coding that the main modules of OpenSpace are developed in. Another interesting feature is this parallel peer. So this is the concept that you could be running it here in the planetarium, and there could be a planetarium in LA that is running the same version of the OpenSpace software. They can connect to each other, and everything that we do here gets mirrored there. And so this concept of you can give kind of a global presentation. So I can be giving the presentation here, that software could be running in other domes around the world, and they could be seeing the same presentation. And this is a really kind of a compelling feature for NASA and for giving these presentations. I put this slide in just to give kind of a simple overview of everything that happens from when I click to run OpenSpace to when you see something on the screen. So basically, I just kind of want to run through this so that when we're talking about some of the other features, you'll have an idea of where these things fit in to the pipeline of what's happening. So obviously the first thing you do is you double click it, you launch OpenSpace. And then what does that do? It looks for the OpenSpace.cfg file, which is the configuration file. That configuration file tells us which profile are we loading in. Are we loading in a dome? Are we loading on a screen? Are we loading in an Oculus? What is the window resolution? It sets up many other config type of things that I won't even bother like detailing, like what folder do you want the log file to go in, what folder do you want your screenshots to be saved in, all sorts of various config type-y things, and we can look at the file later if we want and see what all of those things are, but most of them you don't really need to use. But an important thing that you specify in the config file is what scene you are showing. So our scene file is the first thing that is read by the OpenSpace engine that says what do they want to show. So in the scene file, you add in all the different things you want to show. So you add in the universe, you add in the planets, you add in spacecraft. You add in all these things. You set up different key bindings so that when you press G, it focuses on this guy, and when you press M, it focuses on this guy. And I will demonstrate a scene file later. The scene file includes many asset files. So every different thing that you saw on the screen has an asset file associated with it. So Earth has an asset file. Moon has an asset file. The Mercury magnetosphere has an asset file. Mercury itself has an asset file. The Messenger spacecraft you saw has an asset file. So the scene file includes all these asset files. The asset files then specify the renderable. So they specify what type of thing is shown by this asset file. So in the case of the planets, it specifies a renderable globe. In case of the spacecraft, it specifies a renderable multi-model geometry. In the case of the magnetosphere, it specifies a rendering time-varying volume. And so each one, we have all these different types of renderables. The asset file says, hey, this is the type of thing I want to show, and here are the properties for it. And then the OpenSpace engine goes into our modules and says, hey, you are the module who said that you know how to render renderable globes. So now I'm telling you they want to draw this on the screen. You are the module who said that you can add an atmosphere to a planet. So now I want you to put that on the screen. And so we, one of the key features of OpenSpace is this modular architecture, which is the concept that we can add new things and new types of features to OpenSpace by just adding this new module, then adding some assets that specify renderable types that that module knows how to render. And that's how we were able to add in new features like adding in a volume or adding in a renderable spacecraft, right? On our first version, we didn't have renderable spacecraft. Someone made a spacecraft instruments module that registers that type of thing. So I'm going to talk more about the modules, and I'll talk a bit about how they are put together and some of our key ones. Basically, that is kind of the top-down view of how it works, right? Now, what I have here is about how you guys can work on OpenSpace and what are opportunities for you to use OpenSpace to do something interesting. So the top level, but also kind of the hardest version, is these C++ modules. The C++ modules are what add new functionality, right? So an example of a module is globe browsing. That's our biggest module. That's what lets you go onto the surface of a planet and see it. Another module is the volume module that lets you render that magnetosphere. I don't know if you saw when we were viewing it, but it had a really interesting shape to it. That was the data, but it also was rendered inside of a cube, and you could kind of see a little bit about that cube. And that's the way that you render a volume is you have a simulation box, and then you have data that is rendered inside of that box. And so that module handles that. One thing that I didn't mention, but was there when we were on Earth and on Mars, was the atmosphere. So we have an atmosphere module that can add an atmosphere to a planet. It's a physics-based simulation of light scattering. I don't even know the details of it because one of our PhD students at NYU that's his PhD paper on how do you render physics-based atmospheres for scattering the light, or etc. But that's an atmosphere module, and so you specify an atmosphere asset, and I think maybe that's one of the ones I'm going to show later. So these modules are what add the functionality, but I would expect that most people are not going to be adding new modules to OpenSpace because it's the most in-depth and involved way to add something, and it also requires the most amount of OpenGL and C++ coding ability, right? So we have a number of other options and alternatives and basically different avenues that we can use to add things to OpenSpace. So one example is our web GUI. So you haven't seen the interface that I was using, but we are also developing a new interface, which will be released in our next version coming in 2 or 3 weeks, where we actually have a web browser living inside of OpenSpace that is rendered on top of the rendering, and it provides a GUI that is based on web technologies. And so if you have done web development, you could add new features to OpenSpace by just adding things to our web GUI. You could also create alternative interfaces using just web technologies and embed them with we use the Chromium embedded framework. I'll talk a little bit about that later. Another interesting avenue is our socket API. Well, so this is the concept that we have like a web socket running in OpenSpace, and you can send and receive data through it. You can use this to create interesting types of interactions, doing something like a Arduino or a different web page, or I'll talk a little bit more about that later. One of the main ways that people add things into OpenSpace is just with our assets. So we have existing visualization types such as spacecraft, globe, atmosphere, all these volumes, things that I've been mentioning. You can add something new into OpenSpace that is one of those types by just creating the asset file, saying where all the things live on the hard drive, and then it just shows up. And that's one of the things we're going to show. So the assets create the globes and the spacecraft. The globe browsing data is really also another both like compelling and easy way to get stuff into OpenSpace. This is the concept of adding those maps to the globe. So whether it's the new global map or just one of those small insets like the Apollo 15 landing site, these things exist all over the internet. I have a list of like 20 links where you can get these things from, and there's like really a lot of interesting stuff. We're adding new things into OpenSpace through the Globe browsing all the time. And then just another example is like a Spout output. I don't know how many people are doing visual graphics types of things, but basically Spout is this program that lets us take the visuals of OpenSpace and send them to another software. And I'll talk about some examples of what you could do with that later. And then, you know, I kind of wanted to just leave this, of course, because these are some of the avenues that I've identified of here's some easy ways to get things into OpenSpace, but really, I would hope that maybe you guys think of something else. Hey, I want to do this. Like, do you know how I could get that into OpenSpace? Well, yeah, then we can talk about it and figure out how to get that in. So I would encourage you to not say, oh, I have to do something that's one of these 6 things. You can do something that's one of these 6 things, but if you think of something else, it can, you know, OpenSpace is open source, it's extendable, it's modularized. Pretty much if you can think of it, it's possible. Is it possible in a week in a hackathon? I don't know, but we can talk about that and figure it out. So now to get into some specifics, I'm going to talk about the scenes and the asset files and how they're created. So I mentioned the Lua scripting, right? So we have a Lua interpreter in OpenSpace. The asset files, when I open them up, they look like text files. They look similar to a JSON file if you've seen a JSON file before. But the asset files are actually Lua script files. And that does allow us to do some interesting things inside of them. A scene, so the asset files, the scene files, the mission files, the config files, everything is just a Lua script. And our suffix that we add, .scene, .asset, that kind of tells the system how it's going to be used, right? So the scene file is a top-level asset, is a top-level file that gets loaded when you first launch OpenSpace, and it includes a number of assets. It sets different key bindings for that scene. It adds different interesting things onto the dashboard and onto the screen and says to the interface, here are the things that people are going to be using when they're using this scene. So when we're giving the example of the Mars rover, the scene file adds in buttons to focus on the rover and Mars, and it doesn't add in buttons to focus on Mercury and the Messenger spacecraft. Because if you are in the scene for the Mars rover, why would you want a button that easily brings you to looking at the planet Mercury? But when you're in the Messenger scene file where you're showing all the data for that, you don't want a button that shows in Mars. You can add some custom configuration and things that happen on the initialize and deinitialize. So now I thought I would just show the scene file briefly. So here I have the default scene file loaded up. I'll try to make that a little bigger. And then I want to briefly show the default scene file, and then I want to briefly show one of the mission scene files and show how it's slightly different because we've included different things in it. So the first thing that we do is we load a couple helper scripts that are used by different files. You'll probably just want to put that at the top of your scene file if you're making a new scene. Then you can see we say, okay, we need to include the spice data because we're going to want to position things. And then this is the default scene, so we're including all this stuff. We say, I want to include the sun. I want to include the planets. I want to include Mars's moons. I want to include Pluto and its Pluto system. I want to include the digital universe. So if you remember when we were up there, I relaunched from the messenger scene to our default scene. That's because the messenger scene didn't actually have this line in it that says request all digital universe. So OpenSpace, his engine, didn't include the digital universe files into the scene. So they weren't available for us to show. So everything that you want to make available to show, you have to include in your scene file. And you'll see later that all these things that I'm including are actually asset files on the computer inside the OpenSpace folder. So we say all the things we want to show up. I want to show the planets, the solar system, the universe, etc. Then I can say these key bindings, local key bindings. So I've set it that S will turn on and off certain layers and show the night texture of the Earth. I've set it up so that B will toggle the background, the stars in the Milky Way. So if you hit B, all the stars go off. And you hit B again, all the stars come back on. Why do you want that? I don't know. Someone during a presentation said, oh, I'd like to be able to show just the planet and not have the stars in the way. So you can add in just a key that will do something like that. And so for each one of the presentations that we give, we add in these different key bindings. And you'll see that the key binding is actually just a series of scripts that's run when you press the key. So here it's toggling on a layer on Mars. This is doing 7 things all in one key. And this is an example of the Lua interaction where I have a key that then executes a series of scripts which tells the engine do something. Then here I'm including a couple more assets, but instead of just including them up top like I did there, I actually created a variable for it so that I could then reference that variable later. So here you're going to see in the onInitialize, I'm going to use this Earth asset that I included here. So onInitialize, this is what's going to happen when this scene is loaded. It's going to set the time to now, right? Certain scenes want to set the time to 3 years ago. If I'm visualizing the Mars rover and when it first arrived on Mars, I want to set the time back to 2011 or 13 or whatever year it was when Curiosity landed. So in the default scene, we set time to now, and then we actually do this trick, which is we actually set it back 1 day. And this is because we didn't actually have this last 2 months ago, but every time you open the planet, opened up OpenSpace, it defaults to show the Earth, and the Earth had missing images on it. And you said, well, I just opened the program. Is something broken? Why are the clouds not showing up on the Earth? It's missing part of it. Well, that's because those clouds that you saw on the Earth are this temporal layer which loads in today's weather. It loads in yesterday's weather. Well, guess what? Today's weather hasn't completed yet because it's still today. So we always had this thing where you loaded up OpenSpace and half of the Earth was missing because only half of today had happened so far. So we actually cheat now and we load up yesterday. So that way we know that Earth is going to have the complete texture around it. You can see I load in the key bindings. I say which things are going to show up as the interesting buttons in this scene. And then I use that Earth asset to say the initial thing you're looking at is the Earth. Oh, okay.
We have microphones.
Awesome.
Hi, Brian. So what's the default delay then for just like data pooling? Because I'm assuming you're caching or you're
Well, no.
querying.
So I guess there's like there is no default. And what I mean there is every different piece of data point or data set is handled by a different module, and that guy can decide, do I load today's, do I load yesterday's, et cetera, right? So in the case of the temporal globe browsing layer of the Earth's clouds, we know that we needed to go back to yesterday. But then if you talk about the data of that map of Mars, well, that's not actually a live data. That one is a static image. So we have a set of imagery that was compiled in 2009, and we just show that over and over. So in that case, the delay is 9 years and it never changes, or it only goes up, right? But one of the things that we had proposed previously for this hackathon might be to add in the Martian weather the same way we have the Earth weather. And so there, they have pictures of the Martian dust, of the surface of Mars with the dust clouds and stuff, and you could add that in a similar way. Well, what is the delay there? Well, that just depends on when does NASA release the data. Do they release it every 5 hours, every day, every week? And so each different mission from NASA has different schedules of when it releases its data. So there isn't kind of really one, oh, everything comes in 1 week after, you know? It's different for every different data point. So here in our default scene, the last thing I was just mentioning is that we point it to the Earth. So that way we started the Earth. I could change this to the Mars asset, which I created up here. I could say something like Mars asset, oops, sorry, dot Mars with a lower, I think it goes like this. And then, now when I start OpenSpace, it would be pointing at Mars instead of Earth. Yeah, go ahead, come on. Yeah.
This one is regarding the variables you're creating. So everything you're coding or configuring is local to the device?
Yes.
Maybe you'll get there, but I'm just trying to understand, will everything always be local to the device? Because you mentioned peer mirroring.
Yeah, I will show the Mars asset in a bit, and we'll show how the Mars asset includes local stuff on the device, but then it also specifies some web URLs where things can be loaded from. Okay, so that's the default scene, and now I'll just look quickly at the New Horizons scene to just show how it's slightly different. So you're going to... We also have it over there, but we just weren't sure if... Okay. Speak now or tell us later. So you can see the first things are the same. I'm including these helper functions. These things are the same, so I'm in New Horizons. I also want to include the spice data. I also want to include the sun. I want to include the planets and the stars. But I'm also now including this mission of the New Horizons, right? And then I'm setting different key bindings, because when I'm giving the New Horizons presentation, I want to have keys that easily focus me on Pluto or Charon, right? Normal people don't need a key that focuses on Pluto. When you're giving the default presentations in OpenSpace, or you're talking about Mercury, why do I need a key that focuses on Pluto? I'm never going to focus on Pluto. But when you're launching in New Horizons mode and it's all about Pluto, then you want these keys that make it easy for you to give your presentation, right? Because a big part of OpenSpace is visualizing it, but visualizing it to present to people. Take the scientific data and present it to the public. And so we use these key bindings as a way to make our presentations more smooth. And you can see there's various different key bindings that do different things, and I don't need to go into like what each one does, because you can open this up and look at it if you want and see. So what else does it do differently? It registers dashboard items. So when I launch OpenSpace, you guys didn't see, since we were in presentation mode, you guys only saw the visual rendering. You didn't see what was on my dashboard and my menus. You might have heard I was telling you, oh, we're at this time, we're at 2011, May 17th. Oh, we're this far away from the thing. Well, the dashboard tells you those things, and as a presenter, you can use those things in the dashboard to tell the people what's happening and what you're doing. So here, they're registering the New Horizons distance. So what is the distance of the spacecraft to Pluto? And as the mission evolves over time, you can say, oh, now we are this far away, now we are this far away, and you can use that to explain why the pictures are coming in quicker or faster, etc. Another thing, what does it do? It sets the time, right? So in the default scene, we set the time to now, but when we're launching in the New Horizons scene, we want to set the time to July 14th, 2015. That was the day that it was approaching Pluto, and it's at 8 o'clock, which must have been 12 hours before it approached or something like that. Go ahead, yeah. Hold on, yeah, for the stream.
For people that may not know when a mission is occurring, do you have a quick lookup table so that you can go, oh,
yes.
Horizons is this date, and Apollo 15 was that date?
I don't have that lookup table, but when you are creating this scene, right, you're putting together a bunch of assets. Those assets may be the Apollo spacecraft. And how are you going to position the Apollo spacecraft around the moon? You're going to use a NASA spice file, which they've provided, which gives the position of a craft at certain times. There are tools that can then look into those spice files to tell you what date windows are in there. And so that's how I determine those things. And I don't know if I have those tools loaded up on this laptop, but I can see. But basically, you kind of have to look into the data is the answer, right? And so we build those into the scene file so that when you launch the scene, it's already there. But if you were to create the scene file, you would have to figure that out. But you would probably want to figure that out anyway, because when you're specifying the trail of the spacecraft, you have to specify the dates, and we might look at that. So that's about it in terms of here. We're setting the focus on New Horizons instead of the Earth or instead of Mars. And it's just an example of how this scene file is slightly different than the other one because it includes different things and it sets some different properties. Yep.
Hey everybody, so I got 2 microphones. If you have a question, just raise your hand. I'll run over and hand one of these to you. You can just rattle off.
So when you were loading the assets at the top of this file, you had a request all and a require. Like, what's the difference?
Yeah, so I didn't really talk about that just because the difference is not kind of important really. Request versus require, it means that require means that if the file is not present on disk, crash the program. Request means if the file is not present on disk, just ignore it. Exactly. So to be honest, I don't really know why we have require. When would I want an asset that I'm including? But if it's not there, oh, no big deal. So it should be there, right? If it doesn't show up, put the file there, like what? So I don't actually, to be honest, I don't know why we even have built in this request versus require. To me, everything should be require. If you haven't provided all the assets for me to show this thing, why would I show it, right? It's going to look broken. Something's going to be wrong. So, yeah, so as someone new to the project, I've also been wondering, why do we have this, Okay, so that was a little bit about the scene file. Now I want to talk a little bit about the asset file, which is going to look similar at first, but then you're going to see is actually quite different, right? So the asset file includes any resources that we would need. So in the case of a spacecraft asset file, it includes the model and the textures. Yeah, go ahead.
Yeah, just a quick comment, really. I think the require and request thing might be a way to just prevent the crashing. Because when you're loading files, like, it's going to run through each line. So if you have something that's needed and it's not there, but you still want to load the next thing, maybe that's why they use request as opposed to require. Because otherwise you wouldn't go to the next line.
That's exactly the idea. But kind of what I was getting at was like, if I'm setting up this like visualization of the New Horizons mission and I have the spacecraft going and taking the pictures, why would I then say, oh, include this thing, but if it's not there, no big deal, just don't show it, because then I'm going to be giving my presentation and something's going to be missing. I'd almost rather it crash, so that way when I'm starting it up, I know, oh, something is missing. It's not going to be there when I present. But different people have, so exactly what you said is why we have that. I just don't know who would want that. That's for me. Sometimes we build things in that, oh, we want this capability because of course it should be able to do that, and then you realize, well, yeah, it should be able to, but no one's actually going to do that, And this is a common pitfall in software engineering. You might have heard this, you aren't going to need it thing, right? Sometimes people build stuff in that you don't need, and because we're engineers, we want to create these capabilities, and we want to make it the right way, and, so there is some stuff like that. So, let me just run through this. It includes the resources. They might be synchronized. The asset file defines the renderable and might include other assets. I'm just running through it because I want to show it, and it's going to make a lot more sense. So I put here as an example to show the constellation asset because it's a simple one. So let me show that one. So this is the constellation asset. You guys saw the constellations when I turned them on. So this asset.synchronized resource. So when you download OpenSpace, you download a 150 megabyte application. It's very small. But then the first time you launch it, it synchronizes a default set of resources that you need to show the program. So these are where are the stars, the spice files, the pictures of the Earth, all the kind of stuff that you would need in the default scene. And so in the case of the constellations, in order to show the constellations, I must include the data file of where they are, this spec file. And so
this thing right here tells OpenSpace when you start, if this spec file doesn't exist on the disk, go and download it. And so the idea here is that, well, we could have made a 5 gigabyte download instead of the 100 megabyte download, but then what about the New Horizons? That has another 3 gigabytes. And what about this guy? He has another, and all of a sudden now our download is 20 gigabytes. So what we do is the first time that you use a resource, we synchronize it onto your computer. And if you are never going to use that resource, we never download it for you. So if you are never going to show the New Horizons spacecraft, we never download the model of it for you. And the way that that happens is the first time that you launch, including the New Horizons asset, it would have a synchronized resource that for the model, and that would download. And so when you'll see when you put OpenSpace on your computer and run it, the first time it's going to download 4 gigabytes of stuff. Then the next time it's going to download 0 gigabytes until you switch scenes. So synchronizing the resource is an important part of any asset. And then here we can see the actual specification of the renderable. So this is basically I've said I'm including this resource, and now I have something that I want to show on the screen. In the case of the constellations, I'm going to show this thing which is a renderable DU mesh. What is that? Well, that's just what they called something that shows the stars and shows in the plane of the stars. DU stands for digital universe. So by default, it's not enabled. So all these things are the different properties, and these things will show up in the menu of things that you can adjust. So by enabled, false. So when I launch OpenSpace, the constellations are not showing. The way that I showed them was I went into the menu and I clicked on the checkbox for enabled, and it set this value to true, and now it showed up. So everything that you see here is a property that then shows up in the GUI. And how do you know what properties are available for what type? Well, the renderable type specifies which properties it has. So when you, either you will look at other assets of that type. So when you want to see what properties can I set for a spacecraft, you'll look at a different spacecraft file, see what did they have, and you'll include those things. Or if you want, you can go into the documentation of the module for spacecraft and see what it specifies of the different properties. But more often than not, you will look at another example file.
What's unit referencing in this case? The units of the renderings or
No,
the device?
No, I actually have no clue, to be honest. Yeah, you're going to see some of those that's like, ooh, you know, the only guy who knows what this is the guy who wrote the model. Or, in fact, I would say that we can probably look in the documentation for renderable DU mesh, and it should tell us.
Can the line graphics be drawn in perspective? Say you're close to an orbit, and that orbit looks a certain width in the view, but narrows in the distance, the same with
So, I mean, we do, if we look at an asset for a orbit trail, it has a thickness that you can set. However, I don't know if the module for a renderable orbit has the capability to set the width of the trail based upon the distance from the camera. And so my short answer would be no. But I gave that long answer to kind of explain how that capability would be added in. So we have a module that looks at an asset file when it sees the type of renderable orbit trail. It then looks for a property called line width, and then it knows how thick to draw the line. But someone could go into that module and in the draw method look at the camera position and say, if you're this far away, like the width should be a multiple of the distance of the camera. And so while that's not something we have now, that's the type of thing that you could extend by editing the module itself. And to be honest, maybe that capability is in the module. I've never seen it, right? So then the last kind of thing that a asset file specifies is where it should show up in the menus. So here, the constellations show up under Milky Way, but you'll see later a planet shows up under planets, solar system, planets, the name of the planet. The spacecraft might show up under missions, the name of the mission, the name of the spacecraft. And I'll show I just wanted to show this constellation file because it's just a small one chunk, but I'll show a spacecraft file coming up. Okay, now let's go back to here. Okay, so the SPICE data, I just talked about it a lot of times. I just kind of wanted to bring this in just to briefly mention what it, it's their acronym. This is the data files that NASA produces that gives this spacecraft, planet, instrument, orientation, events data. So basically, where was the spacecraft as given a function of time? Where is the planet as given a function of time, right? So that's this, what they call the ephemeris data. This is like where it is, when. Then you have the instrument data. So what instruments are on the spacecraft and when are they firing? So that data is what we used in order to show the view frustum of the New Horizons craft. And when it puts a picture on, we know when it's taking the picture because we have this data. It says they took a picture at this time. They took a picture, this camera fired at this time, this camera fired at this time, this camera fired at this time. So we can use that to draw a line from the camera to the planet at the specific time. The C file is the C matrix, it's the orientation of the spacecraft, right? If you are visualizing the spacecraft orbiting around a planet, you don't want the camera pointing away from the planet because then it looks wrong, right? The heat shield has to be facing the sun. Well, how do I know how to rotate the spacecraft so that the heat shield is always facing the sun? Well, guess what? NASA provided us with the exact rotation of the spacecraft at any given time. And so it includes all these different types of SPICE kernel files, SPICE kernels. And I mean, learning about the SPICE data, you could spend a year just learning all about that and figuring it out. And there's tools available. And, as I joined the project, I've been learning about stuff, and I can show you guys some stuff that I do know, and there's going to be some stuff that I still can't figure out. And it's a complex but powerful system. Luckily, we have a SPICE engine built into OpenSpace, so kind of really all you would have to do is download the files and put the file names in the asset, and OpenSpace handles the rest. So that's really nice. But this is all the spacecraft assets are used the SPICE file. So now I'm going to demo the Voyager asset file to show, you guys heard of Voyager, just to show how we put that into OpenSpace. So again, we synchronize a resource. We say that the first time they try to show the Voyager mission, please go and download the Voyager model, right? We want to show this 3D model. It's an OBJ file. Then we say, oh, also we need the SPICE data. We need to know where Voyager was. So the default person who runs OpenSpace, it does not download the SPICE data for the Voyager craft, because if you're not showing Voyager, why would you need to know where it was, and why would you want to download this 500 megabytes of extra data? Well, you wouldn't. So it's not until you include the Voyager asset in a scene that the data would be downloaded when you launch OpenSpace. So here is where we do that kernels thing I was talking about. So we went to NASA's SPICE data website. We downloaded the kernels for Voyager. We included them on our server so they could be downloaded. And then we listed the ones you need. So we have the frame kernel. We have the, I think this is the clock kernel. This is the binary spacecraft position, more spacecraft position. This is the binary pointing file. And so we specify all those files. And then we specify our asset. So we do an interesting thing with some of our models and spacecraft because of how we are able to render models in OpenSpace. Right now, our model rendering has a somewhat of a primitive limitation in that we can't render model files using the regular MTL material textures that you might get if you just exported something from Maya or from Blender. We can actually only render models with one texture file, like a PNG texture file attached to it. So what we'll do sometimes if we have a model that has multiple textures, we either have to take those multiple textures and bake them into one file, or we can separate the model into 3 pieces, and then each one gets its own texture, and then we can tell the asset file, move all these 3 pieces together So that way, they look like they're one model, but it's actually 3 models that are all moving together. And I believe that that is what happens here, which is why I mentioned that. So if we look at this Voyager here, we're not actually specifying a model file. And that's because this is this invisible node that gets moved around, and all the model files get attached to this invisible node, and they move around with it. So here, we specify a SPICE translation. What that means is move this spacecraft in space via the SPICE data, and the target, so go in the SPICE data and look for Voyager 1 and move it with respect to the sun. So an important thing about the SPICE data is this concept of where is the position in respect to. So I learned this lesson when I was including the Apollo 8 SPICE data. We were visualizing the Apollo 8 mission and as it goes around the moon. So when I first loaded the file, you would see its trail from the Earth to the moon, and then you saw this like wave of these circles. And the moon was here, and these waves of the circles were moving around the moon. And I said, like, what's going on? This is weird, right? And basically, it was the concept of if you're looking from the Earth, the moon is moving. So those orbits were actually moving with the moon as it moved in respect to the Earth. But then when I visualized the trail with respect to the moon, all of a sudden all the orbits were tight circles around the moon. But then, as time progressed, the Earth moved away from the beginning of the trail. And I was like, wait, I got detached. But it's this concept of an orbit around the moon. If you take a fixed piece of string and then the Earth moves, but that initial starting point of where it started is still the same place, so the Earth has moved away from it. Or when I was reviewing with respect to Earth, the moon was moving through these orbits. And it was really an amazing realization for me, but it was also a lesson to be learned about the SPICE data of what is this concept of the orientations and the transformations. Go ahead, yeah.
So for like all the SPICE data, that is historical data, effectively?
Correct, except there is certain things like the planets, they pre-calculated it. Right. And then certain things like missions, they will actually create a pre-mission SPICE file, so where they think it's going to be and where they're planning on sending it.
So for something like Voyager, for example...
That's historical. But it does include where it is now. So if I launch this scene, I start at 1971, but I can press now, and it shoots Voyager all the way out there.
But if you want to visualize where it will be in 10 years...
Exactly.
You have to do the telemetry for that?
Correct. And the SPICE kernel may or may not include that. If it doesn't include that, and I jump 10 years, then you'll actually see this error showing up in the log that says, unable to calculate position for body Voyager at time, blah, blah, blah. Basically, it's telling we've gone outside of the calculated range. So it would be interesting, actually, for me to go look at that SPICE file for Voyager and see how far does it go. Because I know I've jumped to now, or I jumped to now a month ago, and I saw it, and I said, holy crap, it's out there, you know? So, yeah. So, yeah, the question was, how many missions can you run simultaneously? So, the short answer is 1. And the long answer is, maybe you could run 5, and I just don't know. So the reason that I say that is that right now when you launch the application, you specify which mission you want to show. However, we do have some code, I just haven't really messed with it, that would theoretically let you load another mission into the current mission and be showing both at once. Or you could easily just take all of the asset files for all the missions and include them into one mega scene. And then you have everything at once as one super mission. So if you cheated and did that, you could load them all up, as many as you want, and then, you know, if you put in too many things, maybe your frame rate is slow because your computer is slow. But there's also this concept of right now, all the assets are loaded at start, but we do have some scripting capabilities that will let you dynamically add assets at runtime. However, they are a little more untested, I would say. I've seen them used before, but when I tried it once, stuff just died, and I was like, I don't have time to mess with this. So here, I'm going to go back to Voyager, and I'm talking about how it was positioned. Same thing goes for the rotation. Basically, I'm rotating this Voyager 1 spacecraft, and that's the frame I look for in the SPICE kernel, and I say rotate it in terms of the galactic plane. And then I say, now take this thing and put it in the menu under Solar System Missions Voyager 1. But now you're going to see the renderables. So this is the model of the Voyager spacecraft. So the other thing was this invisible node that I'm going to attach 3 different models to and make it look like one spacecraft. So the first one is the Voyager main. So here, what I do is I have this parent. And so that says, I'm not going to give you any type of position data for this thing, but I'm telling you that its parent is the other thing that I specified. So basically, position and do everything to this guy, basically put him inside the other guy and he'll handle, right? If I put this cup inside of a box and then I move the box, the cup moves with the box. That's what's going on here. So I haven't said where to put it and when because I'm telling you where to put the box and that will handle moving the cup. So this is a renderable, it's a renderable model. It's a multi-model geometry, so renderable model is one of the renderable types that's exposed by one of our modules. So the modules create renderable types that can then be used in asset files. So OpenSpace loads up a scene, the scene includes an asset file, the asset file says, I have this renderable, and then the actual module code draws it onto the screen. I know I'm like already said that stuff, but I'm just trying to reiterate it to include it. And then here I have the antenna. So I had the ship, I have the antenna, and I think that was it. In fact, this is just 2. And this model is made up of 1 model and the antenna, but you'll see some other spacecraft are made up of 3 or 4 or 5 things. So then what I also include in the Voyager asset is the trail. So you heard me talking about the trail before. This is another different type of renderable. It's a renderable trail trajectory. You saw that blue line. That was the trail of the Messenger spacecraft. And so that is how I do that. So I give it, again, the same type of positioning. I give it a color. I tell it when did it start and end. And then that's how it knows when to draw it and where. And here I have it for Voyager going from Earth to Jupiter, and then I have from going around Jupiter, then I have it going from Jupiter to Saturn, and this is how NASA included the data files. So I'm going to just try to speed myself up a little bit, because I'm talking about a lot of stuff. So the modules, so I talked about the assets, and the assets are rendered by the modules. So they provide the functionality of rendering. I kind of maybe already talked about all this stuff, but one of the main key points is that these modules are added all the time by our master's students doing their thesis. So every year we get a few new module types that add new types of rendering capabilities. And so another key point there is some modules are not available as part of the main release. That's because a student might have done their work on it, and it's cool, and it's amazing, and we want to show it, but the code maybe isn't fully up to par with our coding standards, or maybe its functionality breaks a different piece of functionality. So after they finish the modules, then there's a certain amount of time that we have to take to massage those modules into our main code base. So in the case of the Gaia stars, if you wanted to see how we render the Gaia data set, you'd actually have to check out a different branch of our thing, build OpenSpace with that module enabled, and then show that. Why do we do that? Well, because it turns out that you can't render Gaia and the Earth atmosphere at the same time. And until we figure that out, we're going to have to once we figure that out, then we can bring the Gaia module into the main code base. And so there's a couple interesting modules that we have available that if you downloaded OpenSpace wouldn't be there in the download, but you could find them on our GitHub or some of our wiki pages. So I will just literally for 2 seconds demo the module. So I'm just going to show the The atmosphere module, as an example, basically, the module extra large icons really just includes a couple of files. It includes a C++ file, which if I open in Sublime Text, you're going to see is incredibly small. This file just literally specifies what type of renderable. This says, I'm a module that can do renderable atmospheres. Other modules might include multiple types, but the atmosphere module just includes one type, atmosphere. And then it has code for renderable atmosphere. And then in here, you can see what is an atmosphere, and you can also see, like, this is all the code for it, but it also includes documentation of what the different properties are that this module has, that renderables of this type have. So now you know when I'm making an atmosphere, I can specify a average ground reflectance, I can specify a ground radiance emission, et cetera, et cetera. And so, is there anything, and that's essentially a module. It has a piece of code that says what it is. It then includes C++ class for each type of renderable, and then it includes any necessary shaders that you need to do the OpenGL rendering. I will kind of maybe just leave it at that in the interest of time. And I did want to just show briefly that I showed that kind of documentation that was in the code, but we actually have an engine that goes through the code files and generates HTML pages based upon those comments in the code files. And so if we look under here, you know, you can see some of these different things, and you can see maybe this other guy is a better one. And so you can kind of see what the different values are. So this is the one that we saw for the constellations. It was a renderable DU mesh. Well, what type of things do you set for a renderable DU mesh? You could look in the C++ file, or you could look here and you can see, oh, it has a transparency, it has a color. Does it want to draw the labels or not? It has a text color. And so we make sure that this is like one of the examples of like maybe the student file didn't include the documentation. So we have to write that in before we want to include it in our main thing. But all of the classes should have this documentation associated with it. Okay. Let's go back to this guy. Okay. So, so just briefly, like the C++, if you were going to be building your own modules, these are some of the tools you would use. Obviously, you're going to get the code from GitHub. We use CMake to configure the build file, whether it's for Visual Studio or for Xcode or for some Linux build environment. I don't know what people are using on Linux these days, CodeBlocks, CodeLight, whatever it is. But basically, you run the CMake on Mac and it generates an Xcode file. You run the CMake on Windows, it generates a Visual Studio file, and that's what you can use to actually build the thing. For people who are interested in that, I can show it's really just a couple of clicks and then boom, you have it up and running. But I won't go into too much details past that. So here I just said some notable modules. The globe browsing module is one of our big modules. I wanted to talk a little bit about how it works. It uses GDAL and it adds layers to the renderable globes. We have two different types of layers. I mentioned the web map loaded layers, the web loaded layers versus the local layers. So the web loaded ones come from these WMS files. The local ones are the VRT files. The data format for the globe browsing is the format of GeoTIFF, which is a combination of the TIFF file format, image format, combined with geospatial information. And there's a lot of different tools around extracting and manipulating the geospatial information there. We use the GDAL tools. There is another more in-depth set of tools called the AIM stereo pipeline, which comes from NASA. This is taking the raw data files from like the images from that were taken by the spacecraft and creating these digital terrain models and stuff out of those files. We have a series of students at the museum who do that kind of work, but that's a similar type of thing that you could do. Hey, we noticed there's another site on Mars we want to show. You don't have it in open space. You can go download the raw files from NASA's PDS, run them through this AIM stereo pipeline, and get it to show up. So I have all sorts of links and stuff about how to include data with the globe browsing module. I just wanted to quickly show the Mars asset file. So if we look at, I was going to show Moon, not Mars. So the Moon, it has the similar thing of its SPICE translation, but it's a renderable globe. That's a renderable type that's exposed by the globe browsing module. A renderable globe has these different variables, and one of the key variables are these color and height layers. So here we are specifying this is a map of the Moon that I can show, the wide-angle camera that I mentioned. And what we're saying is get the HTTP information from here in this folder under whack.wms. And if I were to open that, which I don't think I included here, you would basically just see it's an XML file that lists a URL to download the tiles from, and it lists like the size, how many tiles are available. And you can see for the Moon, we are listing all these different layers that we have available. And then we do the same thing for height layers, all the different, the Lola one that I talked about. And we can say where does the shadow come from, and then we give it a path in the GUI, and then we export it. So the key part of the globe browsing, of the globe asset file, is what layers are available. So let's go back to here. Maybe I will skip this. This was going to show an example of the files that you would create for adding like the Apollo 5 landing site. I'll leave that for when somebody actually wants to do it. We can go into the in-depth there. The Gaia module is a module that I talked about. So I said the globe browsing module is a notable one. The Gaia module is one that has become popular in the last year because people keep asking, do you have Gaia? How do I show that? Obviously, our GUI module is kind of important because without it, we'd have no menu. And then we have our web GUI module, which is the new version that shows it with a nice web rendered interface. So aside from the asset files and the C++ modules, I had identified a couple other things like web development. So you could either work on our web GUI, or you could make your own web pages that could control OpenSpace and either function as a GUI for OpenSpace or an alternative type of GUI for a different type of thing. So perhaps you want to make a web page that would have 6 buttons on it, and then when OpenSpace is running, you can just press one of those 6 buttons and it would do 6 very simple things, like you want to make the kids interface for OpenSpace. You could use our web technology interface to do that. The socket API is actually what the web GUI technology uses. So basically we have a socket in OpenSpace that you can either pull data from or push data into. We don't have too much documentation for it yet, but I can show people how the web browser uses it. But it can be used for an interesting thing like a Raspberry Pi, right? So if you wanted to make, like one of the things I was thinking would be real interesting is like, let's just say you had 9 buttons, one for each planet, hooked up to a Raspberry Pi and they had colors, and you press a button and you want OpenSpace to then show that planet. The Raspberry Pi could use the socket interface to be connected to OpenSpace. Whenever you press a button, it then sends an event over the WebSocket, tells OpenSpace focus on the thing that I pressed the button for. And so I think the socket API could be a real interesting avenue to do stuff in the hackathon. Spout is another one that I mentioned. So basically this is the concept. You're using OpenSpace, and instead of showing the graphics on your monitor, you're sending the graphics to another program. That program might be a projection mapping software that they use to show those cool projections on buildings. Maybe it's a computer vision software in open frameworks that identifies the stars and highlights them or does something fancy with them. There's actually really interesting things you could do here that I haven't even thought of. We use it to do a 360 video recording using this world viewer software that can take in our fisheye and output it as a 360 video. So while we haven't done much with the Spout, I think there are some interesting things that can be done there. I included some miscellaneous things like scripting. I talked a bit about how the interaction works by executing Lua scripts, but there could be some real interesting things you could do by combining sets of Lua scripts that then call other Lua scripts, and you can create some really interesting like either demos or things like, you know, I made a really interesting educational thing where you just press G and all the planets get scaled by 4,000%, so that when you're looking at the solar system, you can see like, oh, this is what their scale looks like, you know? We have all sorts of other things that we need, like infrastructure, data updating, procedures, testing, so things that you might not think as part of the hackathon, but like, but these are things that are needed. Like we have the Mars rover data, but we only have it from 2013 to 2017. Well, what about last year's? Maybe we need a procedure where it can go to NASA's website, download the new data every month, and then include it in OpenSpace. So while that could be something that happens outside of OpenSpace, it's still a type of hacking thing that you could do in order to bring stuff into OpenSpace. I just listed out some example things. I didn't want to be telling you guys what you should do in the hackathon, but I just wanted to give some examples to like show this is the type of thing you could do with some of the stuff that I showed. So I mentioned the Martian weather thing. That's from the Marcy camera, the Mars something, something, something. The Cassini mission visualization would be similar to our New Horizons or our Voyager. That's one that people have talked about doing or tried doing or whatever. I mentioned the solar system sculpture thing I was talking about with the buttons. One thing that someone actually did recently, but I brought it in as an interesting example, was this Python spec file creator. So basically somebody wrote a Python script, it has nothing to do with OpenSpace, but it generates the asset files that OpenSpace use. So it goes to an online star database, some ESA website, downloads their databases and converts them into OpenSpace's format. And now all of a sudden you could have a different database of stars showing up in OpenSpace. So that's a really interesting type of way to hack something into OpenSpace, but they actually didn't code anything in OpenSpace or use any OpenSpace code. They wrote their own Python code that just generates an asset file that OpenSpace uses. So that is my last slide. Yeah?
I have 3 questions.
Great.
The Python spec file creator, is that something that's available on GitHub? Do you know?
Yeah, it is. It is.
Okay, cool.
Yeah, I have the link right in here in my speaker notes.
Yeah, if you can ping us the link,
Yep.
like on the OpenSpace Slack or something. The second thing is, during the hackathon, while we are using it, if we need help with OpenSpace.
Oh, I will be here the whole hackathon.
Oh, okay.
Well,
Awesome.
yeah, exactly. I don't know 100% if I'm going to sleep here Saturday night, but I will be here Friday, all day Saturday, all day Sunday, available for, like, I will just be sitting here waiting for people to come and ask me. So don't be afraid to come and ask me. And if I spend all day working with you, then I spend all day working with you. If it's 10 minutes, then it's 10 minutes. But I'm here the whole hackathon for you guys.
We also have a Slack team workspace set up, so we can create like an open space channel for people
Perfect.
to post questions.
Awesome.
And so you don't have to run around the entire event. You
Yeah,
can just-
dope. Perfect.
Yeah.
So,
Is that on?
whoops, is it on? Yeah. Yeah.
Here, this microphone's on.
Awesome. Super quickly. Hi, everyone. Thank you for coming out tonight. My name is Camera Walrand. I work with Micah at the American Museum of Natural History on the OpenSpace project. Like Micah said, OpenSpace is a NASA-funded project. We work with collaborators throughout the US and abroad, and we're working on making this free and open source for people just like you. And we want to know how we can make this better, what we should do. Part of the reason why we're out supporting this event is because we want all of your smart brains to put your eyes on this project and work on it and give us ideas. So before you can leave tonight, come see me. I have a very brief 7-minute survey to ask you about how you came here tonight and your experience so far, and it would really help us out a lot. We would greatly appreciate it. Thank you for your time.
It's really just 5 questions. It's quick. Do it if you can. Cool. It helps us for our grant to make more awesome open space stuff.
I also wanted to just point out that a couple of the challenges, so there's 20 challenges for this 2018, a couple of them that at least popped out of my mind that could definitely benefit from OpenSpace, and there's plenty of them. One of them is called Mission to the Moon, so visualizing a mission landing, so on, to the moon. Virtual space exploration, which is both for the moon and Mars. And then the last one is Hello Bennu. So if you were to visualize the OSIRIS-REx mission that is going on its way to the asteroid Bennu, and then visualizing it and introducing us to what Bennu looks like or characteristics of it.
And if you do that, it will help me for a presentation I'm giving in December.
Oh, there you go.
I will be invested in helping you.
Cool. So let's just cut it off there. Thank you guys so much for sticking with us to the end. If you have any questions, feel free to ask afterwards. And also, as I mentioned, we will have the Slack channel open on our workspace for any questions throughout the weekend. We'll have mentors available. And use the hash at OpenSpaceProj on Twitter. Also, if you have any questions. Thank you.
Right. Yeah.